হ্যাঁ, পার্টিসিপেন্টস 80 প্লাস হয়েছে। আর ইউটিউবে কতজন হয়েছে? হ্যালো,
আমি ইউটিউবে স্যার দেখছি না। শুভদীপ
40 প্লাস চলছে, বাড়ছে।
তো তাহলে ইনিশিয়াল কাজগুলো আরম্ভ করা যেতে পারে। ঠিকই আছে, 100 প্লাস হয়ে গেছে, 120 30 টোটাল। 87 প্লাস 40, 130 অ্যারাউন্ড। বিশ্বজিৎ কি জয়েন করতে পেরেছে? সুদীপ আমার কথাগুলো শোনা যাচ্ছে তো? আচ্ছা আচ্ছা,
তাহলে স্যার স্টার্ট করি।
হ্যাঁ হ্যাঁ, তোমাদের ফার্স্ট রাতে থাকতে পারিনি, ফার্স্ট ওয়েবিনারটা থাকতে পারিনি।
Okay, good afternoon.
হ্যাঁ, স্টার্ট করো।
Good afternoon and welcome to all in this webinar. We are celebrating 175th anniversary of our esteemed institution, Krishnagar Government College. As a part of this, as well as energize and motivate our students in this pandemic situation, and also to engage ourselves, we are organizing a series of webinars titled Discovering the Fascinating World of Physics. Today's one-day national level webinar on exploring the sky from Aryabhata to Chandrayaan is the second chapter of that series. Wow! I think all of us uttered this word, which summarizes our feelings after viewing the magnificent sky with all the amazing constellation, meteors, and comets moving around, and the exposure of dots of light far too numerous to be ever counted. The sky, a mystery to all, attracts us equally, and we are eager to touch the sky. This curiosity and our power of thinking get birth to a new branch of science, space science. We all know about ISRO, Indian Space Research Organization, which is the premier space agency under the Department of Space, Government of India, headquartered in the city of Bangalore. In 1962, by the efforts of independent India's first Prime Minister, Pandit Jawaharlal Nehru, and great visionary scientist, Vikram Sarabhai, Indian National Committee for Space Research, INCOSPAR, was established. And later on, in 1969, ISRO superseded it with the mission of providing the nation space-based services. ISRO built India's first satellite, Aryabhata, which was launched by the Soviet Union in 1975. Few years later, in 1980, ISRO placed Rohini in its orbit by an Indian-made launch vehicle, SLV-3. Since then, ISRO accomplished various remarkable and successful missions like Chandrayaan-1, Mars Orbiter mission, etc. And in recent past, Chandrayaan-2. We all can't forget the day, 6 September 2019, the last minute tension of landing Vikram on lunar surface, a part of Chandrayaan-2, loss of communication with Vikram, and the fears of ISRO chairman Shivam sir. Though at the time, the common people thought the mission was failed. Later on, it is revealed that the mission was very much successful. Today, We'll hear all those real stories and challenges from Mr. Amit Maji, scientist SF ISRO Bangalore. I'm sure this webinar will motivate our students to touch the sky. To organize this webinar, we are thankful to our respected officer in charge, Dr. Shobhar Niyogi, Associate Professor in Chemistry, and IQA Coordinator, Dr. Amoris Mondol, Associate Professor in Bengali. We cordially welcome them. We are very grateful to our honorable speaker and very pleased to welcome Mr. Amit Maji, Scientist SF ISRO Bangalore. We also cordially welcome all the participants to make this event success. We have arranged you to live streaming apart from Google Meet platform to accommodate as many participants as possible. We request all the participants to mute their microphone and video and not to share the screen so that webinar can be conducted smoothly. Any query about this lecture may be communicated through chat box in Google Meet or YouTube Live. Now, I'd like to request our honorable officer in charge, Dr. Shobhar Niyogi, to deliver his welcome address. Please, sir.
Okay, thank you, Dr. Hui. Namaskar and good afternoon to all of you who are present in this webinar. Today, Physics Department is organizing its second webinar on the topic Exploring the Sky from Aryabhata to Chandrayaan. I welcome our distinguished speaker, Sri Amit Maji, scientist ISRO Bangalore, from whom we will be enlightened to know the fascinating world of the sky and the story behind how to explore that. I welcome my colleagues from my college, my beloved students and teachers and others from other institutes who have joined this webinar through Google Meet or YouTube telecast. I welcome them all. Our college was established in the year 1845, November 1845, that is 175 years back. So that's why we are observing the establishment of this college as its 175th establishment year. We planned a lot. We inaugurated the process of observing this in November 2019 with a very glorious functions. The sports system continued, but suddenly from March this year, as we all of us know, this pandemic has seized everything. The academic activities, the regular activities. In India, one statistic says that about 35 crores of students are affected due to this pandemic. So we are not exception to that. So the main stream of academic activity has come to a halt, but the regular online classes, as far as possible, our teachers are taking, and we initiated this sort of web-based webinars about 1.5 months back. And during this 1.5 months, we have almost organized 20 such webinars where various scientists, doctors, senior professors, executive officers of other organizations have provided their valuable time for us to continue with our academic endeavor at the highest level. I once again welcome Sri Om ISRO Bangalore in this webinar, and I now hand over the microphone to my colleague, Dr. Amoris Mondol, Associate Professor and IQAC Coordinator of our college, to say something about this webinar. Thank you all. Dr. Mondol, please.
Thank you. Good afternoon, everybody. It's my honor and privilege to have been asked to say a few words in this one-day national level webinar, Exploring the Sky from Aryabhata to Chandrayaan, organized by the Department of Physics. On behalf of Internal Quality Assurance Cell, Krishnagar Government College, I would like to express my hearty congratulations to Dr. Bishwajit Pal, Head of the Department of Physics, and his very active departmental colleagues for organizing two national level webinars within a short period. I am happy to observe that at this pandemic situation, all head of the departments along with all faculties have been trying to maintain academic activities as far as possible in our institution. Now, I would like to convey my sincere gratitude and regards to our distinguished speaker, Sri Amit Maji, scientist, ISRO, Bangalore, for giving his kind out of my heart. This webinar discussion will surely enrich all the participants. I am a success of today's webinar. Thank you. Thank you, everybody.
Thank you. Thank you, Dr. Amoris Mondal, for being with us as always. Here we conclude the inaugural session. Now we proceed to the technical session. And I would request Mr. Arjun Das to introduce our honorable speaker, Mr. Amit Maji, scientist SF, Bangalore, ISRO. Over to Arjun Das.
Good afternoon, everybody. First, I want to thank Arjun for nice introduction, and I take this opportunity to thank the organizer committee, Krishnagar Government College, to give me this opportunity to speak about Indian space program, past, present, future. I think I'm audible to everyone.
Yes, you are audible.
Okay. So whenever we start our Indian space program, we need to know two great scientists of India. One is called Father of Indian Nuclear Science, and he is the first chairman of our Atomic Energy Company, and he was the founder of the TIATAR, Tata Institute of Fundamental Research. This is one of the great institute of India as well as the world, and he is Dr. Hamo Jahangir Bhabha. Next person is called the father of Indian space program, and he also first chairman of ISRO. He established physical research library at 1947 at age of 27-28. He is Dr. Bikram Sarabhai. And when 1950, when the going on between USA and Soviet Union, that time Department of Atomic Energy established by Dr. Homi Jahangir Bhabha. And if you think about Indian space program, it started in 1962. Then our first Prime Minister of India, Jawaharlal Nehru, established the Indian National Committee 1962. After steadily and slowly, this INCASPER converted to the Indian Space Research Organization, that is 15 August 1969. Actually, 1971, after sudden death of the Dr. Bikram Sarabhai, another two great scientists taken the ISRO to the another level. They are Dr. APJ Abdul Kalam and Dr. Satish Dhawan. Whenever Dr. Bikram left, they are taken from there and taken to the ISRO bigger height. Now, if you think why we record the space program, so as quoted by Dr. Bikram Sarabhai, we must be second to none in the application of advanced technologies to the real problem of man and society. What is the meaning of this? Whenever any problem will come to society, we should use the advanced technology to solve this issue. That means we should know the advanced technology, we should develop the advanced technology. Using this vision, we started our space program, and we keep our space program mainly three objectives. First objective, telecommunication. What means ISRO have given more than 200 transponder to the country to for television, detached broadcasting. And if you see the like where there is no education, no college is there, no hospital is there, how they get the benefit for the our space program? We have developed the tele-education, telemedicine communication system. From there, they can connect to the any big city, big hospital, or any institute for that education or medicine. Or telecommunication system, quite a disaster management system. Like if you go to remote village, there is no mobile connectivity. Through this our communication satellite, we can provide that connectivity like a satellite phone. So this is our main objective for telecommunication or geo satellite program. Now come to meteorology. When you think about that weather forecasting, if you think old, like before, we used to use the ground-based system like radar. Radar only give the weather forecasting maybe the 10 to 15 kilometer, 50 kilometer away, but this is very short time. But using the satellite, we can forecast the weather from 2-3 days advance. And from satellite, continuously monitoring the cyclone formation, speed of the cyclone, and movement of cyclone. Very accurately can predict. If you see present cyclone like Phony and other cyclone, we predict the cyclone movement every day by day, and prediction is perfect. 99% is perfect. So how is possible? Our meteorological setting 36,000 kilometers above, and continuously monitoring that weather, that cyclone formation and that strength. Now, next is coming remote sensing. That is a very big area. We are working on that. So, what do you think by remote sensing? What remote sensing are doing? Remote sensing means is acquiring the information from distance. Here, what from distance? We from satellite, we informing some information Earth surface. That way, we have some sensor in the satellite. This sensor detects something. What it detect? It detect the reflected and emitted energy from the Earth's surface. But very large electromagnetic spectrum from gamma wave to the radio waves, but we cannot use all the wavelength. We can use only particular few wavelength that is transferred to the atmosphere. Normally, our remote sensing application, we not using that gamma and X-ray because this is the not transparent to the atmosphere. So we are using from that visible light. This is very small portion of the wavelength to the radio wave. So this wavelength we measuring from satellite and give the information of the Earth surface. Now this measuring also two types. One is the passive measurement, one is the active measurement. What is the passive measurement? You know, sun is the main energy source for our Earth. What they're doing? Sunlight falling on the Earth's surface and reflected back to the satellite. That is the Earth albedo. But the reflected light depend on the reflectivity of the surface. Different surface having different reflectivity, that means different light will come. You consider like snow. Snow having 90% reflectivity. What will happen? If you throw the light of snow, it reflect 90% energy. So our passive sensor measure that energy and detect this is snow. In case of water, sea water, this is having 6% only. So if you light fall sea water, only 6% energy come from the this is the water. So we can do using remote sensor, we can do full mapping of the our Indian region as well as the world. Next, the active sensor. If night we cannot do this passive measurement, so we go to active sensor. Active sensor. The active sensor having the own energy source, like radar. They are sending the energy to the Earth, and this energy reflected back from Earth and captured this. That we are developed the active sensor like RSat-1A, RSat-2B sensor, 2B satellite, and if you see, they can day night. They can observe day night. If you see the passive observation, active sensor, there is no limitation. It can work day, it can work night. So what are doing using this measurement? We can do the land, sea surface temperature measurement, property, cloud erosion property, and other physical property. From there, we can give the prediction how much crop forecasting prediction we can give. We can do the high resolution camera like a sub-meter resolution. We can give the resolution images also. So this is the one big application for remote sensing. Now, if we think the how we can divide our space activity, we can divide the space activity main three category. On a launch vehicle activity, here what are we doing? We are designing, developing, qualifying that launch vehicle, aerodynamics, onboard computer. We develop this, and launch vehicle main activity is the fuel. That means we are developing solid fuel, liquid fuel, as well as cryogenic fuel. Cryogenic is only in the fourth country having this technology. It is a liquid hydrogen, oxygen together give the fuel. For this activity, we are having mainly 4 centers. First is the BSCC, that is called Bikram Saroi Space Center. This is at Trivandrum. Next, the Liquid Propulsion Center. This is at also Trivandrum. Next, the IPRC. This is called ISRO Propulsion Complex. Here only you are developing the complex technology like cryogenic engine, and this is one of the best center in the world to develop cryogenic engine. Now, after this development, we are going to see SDSC sir. This is called Satish Dhawan Space Center at Sriharikota for launching the satellite. So all integration at going on SDSC sir. This is the main center for launch vehicle activity. Next, coming to the satellite activity. For satellite design, development, and qualification, we are doing normally URSC, that is called Rao Satellites Centre. And satellite having payload, that is, I think remote sensor that will be sitting the satellite. That is developed by SAC, that is called Space Application Center. This is Aryabhata. And for satellite, we need a lot of sensor, attitude sensor, that is probably where I'm working. Now, this is called space segment. If you see the ground segment is a very big segment. There we need lot of antenna to capture the signal coming from the satellite. And for control system, we need control system, the controlling the satellite. If you think Mars mission, Mars having almost 80 million kilometers away from the Earth, what signal coming from Mars is very weak. So we need very big antenna to capture that signal. That way we develop the 32-meter diameter antenna at Bangalore. And this can capture a signal from not only Mars, Venus, Jupiter, and interplanetary mission also there. This can capture a signal. So we have many satellites, many antenna, many control center. If you see main control center MCF, that is the at Bangalore. This is called master control facility. Here mainly we are controlling the communication satellite. Then one is the stack, that is the normally we getting the low orbit satellite. NRC. Here all the payload data go there and they processing, give the output, the final product we deliver to the end user. Now come to the launch vehicle program. Okay, it started 1963. First, we established the Tumba Equatorial Rocket Launching Station at Trivandrum. And it is a very, Tumba is a very small village. They call it sleeping village. After that, first launch happened 1963 in November. And but this is not Indian made rocket. This is imported from the Russia. And it is a very simple rocket. It is two-stage rocket. It's very simple, like our DLE rocket. You go to the, if ignite that, you go to the space. After its ignition is fuel over, it will fall to the sea. And but we getting very good information upper atmosphere, ionosphere. We did a lot of experiment on that. Then if you see the Indian started 1965. At 1965, we established on a solid propellant division at Trivandrum to develop the solid propellant, and that is called Rohini series, Rohini project. Under this project, we developed the first Indian-made rocket, 1975, and it is the diameter 75 meter. And we have done almost 1,000 to 2,000 sounding rocket we launched to getting the lot of information from the atmosphere. And presently also we are doing sounding rocket is for a new technology development purpose, that is called Rohini 200, Rohini 300. This platform give lot of exposure, like we develop new technology to mature the technology. First we launch sounding rocket, we prove that characteristic, then use the actual launch vehicle. Actually, if you see the what is the if you see 1963, 62, when that INCOSPER established, there is no land for ISRO. So land ISRO taken a small church. You can see the picture on church. This church handed over for first Tumba Equatorial Rocket Launching Station. If you go to Trivandrum, still you can see the church. They converted the church to the museum, and this is the site of Arabian Sea. And that time there is no vehicle to carry the rocket parts, anything. They used to use that cycle as well as that cow cart to use that way. If you see, ISRO initially started a very humble beginning. And if you see the left hand corner picture, this is our sounding rocket launching station. That is very simple rocket singer. There is a small cover is there, and only a small and this is manually they used to launch that. Now, if you think about our launch vehicle development history, after launching the sounding rocket 1975, ISRO want to develop their own launch vehicle. That way they started SLV-3, that is called Satellite Launch Vehicle. And it can carry only 40 kg payload to the low Earth orbit, that means 400 kilometers to the Earth surface. After few success, few failure, they augmented to the SLV, that is called Augmented Satellite Launch Vehicle. They want to increase increase the payload capacity from 40 kg to 150 kg. So they augmented the SLV-3 to ASLV. That also we get mixed success, mixed failure. But real success started when develop PSLV, Polar Satellite Launch Vehicle. And this can carry a 1,860 kg of payload at 475 kilometer orbit. And this is called Orthros of ISRO. And this is the main Polar Satellite Launch Vehicle available in ISRO. After that, ISRO think we can launch the satellite only lower orbit, but whenever to launch to the geostationary communication satellite, we need bigger launch vehicle. That time we want to go to the foreign launch, but ISRO taken the initiative during 1990 and 2000, early or 2000, we developed the GSL Mark III that can carry 2,200 kg of payload at GTO, geotransfer orbit. But what a from PSLV to GSLV, that is the cryogenic engine. PSLV is the solid motor and liquid motor, and cryogenic engine is used for the GSLV-3. That only initially is to get this cryogenic engine from the Russia. We don't have that technology. Slowly and steadily, we develop this technology. Now we are the master of cryogenic engine. And after this learning, we develop the GSL Mark III, and this is the called Bahubali of ISRO. It can launch 4,000 of payload at GTO. So latest launch like Chandrayaan 2, Chandrayaan 3, or the coming, it will launch by the GSL Mark III. Now I give a little history of how we came to from SLB to the GSLV Mark III. If you see first, I told this is the called satellite launch vehicle. It is 22-meter long vehicle of payload carrying capacity 40 kg. And if you see first launch having 1979, 10th August 1979, this is failure. This failure not due to the technology lack. This failure is small parts of the launch vehicle not function properly. So there is no single error. Single error can fail the. So we learn from that mistake. Again, we implement the mistake to the next mission. We get success. That is 1980, and we launch a Rohini satellite in the orbit. That is first Indian make rocket, Indian make satellite in the orbit. After that, again, we think we are the master of the technology, but again, a failure happened 1981-31. So again, we tried, and the fourth mission success. But what is the problem? This rocket, it is made of solid propellant only, and it can carry only 40 kg payload. So next, what we plan? We want to augment it, this satellite launch vehicle to the ASLB. So it can carry 150 kg payload to the our LEO orbit. This is 24-meter long rocket and 1 meter diameter. And if you see, first two launch is a failure only. After that, we get the success. But we think we find out this only using solid motor, we cannot get the good vehicle, because solid motor problem is that if you once ignite, it cannot stop. On-off control is not there. So we try to do the next technology, liquid motor engine. So next is coming Polar Satellite Launch Vehicle. Here we already must have liquid motor, and we use the liquid engine here. That it will make the 4-stage rocket and 44-meter height. And here also first launch is a failure. And after that, success story started for ISRO. After that, it launched 14 among 48 is success. That is called success story of ISRO. And it is the workhorse for the ISRO. It can carry 1,750 kg of payload to the LEO orbit. And I give little bit about this PSLV stages. What is that? I told this is a 4-stage rocket. If you see that down, having the 6 trapon is there. This is called solid motor. Initially, when rocket want to launch, you need more thrust. That given by this surrounding 4 solid motor. And if a middle is called solid, the core motor we are telling, this is the S139 solid motor. S139 means this 139 ton solid is inside. After that, second stage is called liquid engine. This is called and it is using the UDMH UDMH as a fuel and N2O4 as a oxidizer. Again, for third stage will be the solid, and fourth will be liquid engine, and top what is saying that is called payload The air outside is sitting the top of the rocket, and it is covered by the heat shield. Now next develop the geosynchronous launch vehicle (GSLV), and first launch happened April 18, 2001, and this is success. And it is a three-stage rocket, and we introduce cryogenic engine here, and it can launch now around 2,500 kg payload at GTO. GTO means it can geosynchronous orbit. And EPC, we launched 13 GSLV from that 12 are success. This is similar to the PSLV, but only one thing you can notice, that is the cryogenic stage. It is the initially used to take this cryogenic engine from the Russia. After that, Indo developed one cryogenic engine. Then this rocket is using the indigenous cryogenic engine for launching this satellite. Then come the Bahubali of ISRO, that is called Geosynchronous Launch Vehicle GSL Mark III. It is the heaviest rocket ISRO ever made, and it is the you can launch 4,000 kg of payload GTO, and it lift of masses of 640 tons. This is lift of mass of the rocket, and this is three stage, and height will be the 43.43 meter. And we are very lucky, all the launches success for this. First launch having GSAT-19, that heaviest satellite launched by this rocket. Then GSAT-29, and July 22, 2019, he launched the Chandrayaan 2. That is the Indian second interplanetary mission to the moon. If you see, this is also similar to the GSLV Mark II, but here it changes that this three-stage rocket. And if you see side to big booster, that is called a solid rocket booster. This is a 200-ton solid motor. And if you see middle on, this is called liquid motor, that is the L110. This is 110-ton liquid engine. And main thing coming, this is the third stage, that is called the cryogenic stage, that is the C25. This is C25 cryogenic stage, and top is the payload, that is called satellite, that is the mounting by this, launched by this satellite. If you see the explored view of this launch vehicle, what is so? This is on GSLV. If you see, 4 strap-on is there, that is called liquid strap-on, and this is solid motor S139, and this first stage and second stage are connected by the inter-stage connector. Then this is the coming second stage, that is called liquid engine. This is L37.5, that is 37.5 ton. Then even second stage is third stage connector inter-stage, and third stage is the cryogenic engine. And this is called equipment bay. Equipment bay means all that electronics for the containing the launch vehicle sitting there. And this is a payload adapter. Payload is sitting on this, and this is called heat shield. That is cover the satellite from the protect from the Earth atmosphere. Now, what is the future? What I told that launch vehicle developed by now, it is a one time. When that fuel is over, it will work is finished and it fall in the sea. But this part is very costly. So if you want to enable the low cost access to space, we should reuse that launch vehicle, reuse that part. Then only we can minimize the cost. But this is not so simple. When it entered this parts, when entered the atmosphere, due to high velocity and friction with Earth atmosphere, it will burn out. The temperature will go 1,000 degrees centigrade. Any metal like aluminum, iron, it will melt. So we cannot use the common material for this purpose. We need special alloy that can sustain that high temperature, like carbon styles we use. So India is planning to develop that diesel launch vehicle, and this will be like your aircraft. It will launch by EPC, that left side picture. It launched by your launch vehicle, and solid fuel, and you go to the space and do your activity like this docking. You go dock, repairing the satellite. After that, it will come back and land in the sea. So this technology already on demonstration is done at I think 2016 at Sriharikota. This is partial success. We are future. We are planning to develop this technology. Okay, I roughly told about our launch vehicle development activity. Now I come to satellite. When we talk about satellite, we should know what satellite orbit they mean. Orbit means satellite rotating around the Earth. We can divide the satellite orbit according to the height from the Earth's surface. If you think low Earth orbit, when the satellite from Earth's surface around the 200 to 2000 kilometer, that is called low Earth orbit. And what is the orbit period? Or orbit period means one full rotation. How much time you take? It is around 1 hour to 5 hours. If you see, 63% of satellite are sitting in the LEO orbit because this is very closer to the Earth and do lot of remote sensing application. Now, second orbit is called medium Earth orbit. That height from Earth's surface will be 2000 kilometer to 35,000 kilometer. And this is normally used by the GPS satellite. They sitting in this orbit. And this orbit for around 5 hours to 23 hours in between. But very few satellites sitting there. Maybe 6% of satellite is there. Now one more famous orbit, that is called geosynchronous orbit. This 36,000 kilometer above. What is the benefit of geosynchronous orbit? This benefit is like that: if any satellite in the geosynchronous orbit, it will be stationary with respect to Earth. Like if I launch one satellite in India, it will be always see by India. So all the communication satellite is sitting in the geosynchronous orbit because its orbit to 24 hours and Earth rotation at 24, both are match. So it will be constant on the same point. And if you see 99% satellite is lying in the geo orbit, and this is mainly used for communication satellite. One more orbit is available, that is called high Earth orbit, and that orbit period more than 24 hours and height from the Earth's surface 36,000 kilometers. Very few satellites lying that, like Russia, they want to launch some satellite in this orbit. This categorically tells the orbit with respect to height from the Earth's surface. Now come to the orientation. Actually, it is the equator. If any orbit orient equator, that is called 0 degree inclination. If the angle, the orbit plane is there some angle with equator, if 90-degree angle with equator, that is called polar orbit. That means polar orbit rotate from North Pole to South Pole to North Pole. That is called polar orbit. And one more is sun synchronous polar orbit. This is the polar orbit, but we're not keeping 90-degree inclination. We're keeping around 98-degree inclination. What is the advantage of sun synchronous orbit? Whenever it crosses the equator, it comes same local time. Local time is if 6:30 costs India, next time he costs maybe Pakistan, same 6:30 time, local time. So always the same local time. That is called sun synchronous orbit. What advantage of this orbit? This is the lighting condition, all conditions similar to every time. So all our ISRO satellite is sitting in this sun synchronous orbit. And second, geostationary orbit, that is also equatorial orbit. That is normally sitting in the all our communication satellites sitting in this orbit. Now you talk about the how many satellites rotating around the Earth. If you go to the space, you take one image of the Earth. You can see the image like right hand side. If you see first satellite launch, Sputnik on 4th October 1957. After the almost 9,000 satellites launched by the 40 countries. And from there, 5,000 still in orbit. From there, only 2,000 is operational now. Other 3,000, but they are still in the orbit. So it's very dense, and future also coming very things. I think everybody heard the name of SpaceX, Elon Musk. This is the one American fellow. He want to make one Starlink satellite link. What he want? He want to give low cost, high speed internet access to everybody globe. What he planning? He want to planning 12,000 to 42,000 satellite in the Earth. 12,000 to 42,000. And if you look, if he launch all satellite, it looks like the image looks like the left side. This is the first image. He planning from 2022. It should finish before 2022. And second image is planning to near 2030. So this is future. Now I'm coming to the Indian satellite, first satellite, that is the Aryabhata. It launched April 19, 1975. But this is the satellite made by India and launched by the Russia or Soviet Union. You can tell Soviet Union. And this is the LEO orbit and 50-degree inclination. And it is spin stabilized. What is spin stabilized? It actually is Earth rotating about one axis. That means it conserves the angular momentum to stabilize it. That way, satellite also rotate one axis continuously. And that all the satellite solar cell is pasted to generate the power. We pasted solar cell all over the satellite. And this is the only scientific experimental satellite used for X-ray astronomy, solar physics. But this satellite worked more than 17 years. That means first satellite built by ISRO worked more than 17 years. That is called quality and reliability of the next actual communication satellite that is launched called Apple. It launched, I think, launched June 19, 1981. This is also a satellite made by the ISRO and launched by the Kudu, because that time our launch vehicle was not ready. So we depend on the other country like Russia and France. And this is the actual geosynchronous satellite. It launched at this is parking was 102 degrees east. And if it is a satellite, this is one big gray color is that is called solar panel. This is used for generate the power. And if you see top, that is the called antenna. This is pointing towards the earth for the sun. This is the C-band transponder. It provides two C-band transponder. It is work more than two to 3 years. Now come to our present communication satellite of ISRO. If you think after Apple, India launched almost 20 to 30 operational satellite, communication satellite. From there, 15 are operational. If you think Indian National Satellite System is one of the largest domestic communication satellite system in Asia Pacific region, and it provides almost more than 200 transponders in the C-band, C-frequency band, extended C-band, and Ku-band. And this satellite is used for the telecommunication, television broadcasting, satellite news gathering, special publication, weather forecasting, disaster warning. And if you go to space and see the image from the India region, you can see all satellites lying in the geosphere and they're stationary. They're lying there. This is all satellites showing that single picture. Now, well, Earth observation satellite. That is called nothing but remote sensing satellite. They using that remote sensor like different imaging camera to do that one. If you see first, we launched IRS-1A 1988. This is called first remote sensing satellite launched by the ISRO. After that, we launched more than 30 remote sensing satellite. From that, 17 are operational. If we call remote sensing satellite, we divide two categories. One is the sun synchronous orbit satellite, one is geostationary orbit satellite. Sun synchronous orbit, I told this is the polar orbit with 98-degree inclination. Here we have research set 1, 2, 2A, Cartosat 1, 2, 2A, RSat 1A, 1B, 2B. We have many. And geostationary orbit, if you think, we are having 4 satellites sitting there, Insta 3D, Kalpana, Insta 3A, Insta 3D. What is the advantage of geostationary orbit satellite? They can continuous 24/7. They can monitor that weather of ISRO, weather of India region. So that way we putting the satellite geosynchronous satellite. I saw one small photograph video how that image taken by Cartosat. Okay, I first explain this one. This is the image taken by our satellite. First image, if you see, that is the taken by our ResearchSat 1 in the LIS 4 camera. And this is the image of the Manas Sarovar, Tibet region, and taken by the this is first image taken by ResearchSat 1. And if you see right hand side top corner, this is the Cartosat 3 image and Doha. You can see what is the resolution we are getting. The movement of vehicle in the road, you can see here. That is that much high resolution imaging camera we are developed, and this normally used for the defense purpose, and we giving this defense and border imaging purpose, and it gives the resolution of sub-meter accuracy, less than 0.6, 0.6, 7-meter accuracy. And if you see left-hand corner, this is the image taken by Kalpana satellite. That is the setting at 36,000 kilometers above. And this is a continuous monitoring the weather cloud coverage of over the India and give the information to the our Met department. And one more image you can see, that is left-hand. This is the night image of Howrah Bridge taken by our RSAT camera. This is taken not in the visible region, taken by the RSAT, means X band wavelength. You see so clear image you can see. And this is the RSAT 1A used for day-night observation of border and defense purpose. Okay, before that I show one. And if you see, this is the one here.
One is a stereo imaging satellite with 2 cameras on board. Covering the imaging provides 3-dimensional information of the image area. Imaging can be done anywhere on the globe. The satellite has the capability to store the image data and transfer to the ground during a payload station visibility. In X-band frequency, the video shows the stereo imaging in real-time mode as well.
Now we can see that camera, that Cartosat 1A camera taking the study imaging when it come to the came over in the India.
As record and playback
And
mode.
this studio imaging, that means they're using 2 camera. They're using 2 camera to give the studio imaging depth information also.
Mode.
After imaging over, it sends the data to the our ground station. You can see there's data sending by the X-band ground station. And meantime, they're taking the second images, and that also sent by our ground station. One more I want to show, that scatterometer. That is also one.
Scatterometer is a microwave radar, which measures the.
This is normally used for the ocean monitoring. They are being color ocean color monitoring, and the scatterometer. They will measure the microwave radiated by the sea surface, and from that they decode that potential fishing zone. They can find out what the fish is more, and then that information giving the fisherman. The fisherman go there, catch the fish. That is the information given by this scatterometer.
Backscattered energy from the ocean surface, from which wind vector information will be derived, using a geophysical model function. This is a conically scanning pencil beam scatterometer operating at 13.515 GHz. There is a 1-meter diameter parabolic antenna, with 2 offset feeds, rotated continuously at 20.5 RPM. The 2 feeds make.
Okay, I go to the presentation now. Okay, next coming your Indian GPS. Actually, India developed their own GPS system, that is called Indian Regional Navigation Satellite System. It will provide our relevant position, navigation, and timing service over India and its neighbors like Pakistan, Sri Lanka, Bhutan, Nepal. It consists of 9 satellites. From that, 3 is geostationary and 6 is geosynchronous. And if you see, if in future you want to buy any mobile phone, or what do you call our GPS, that is called Navic chip also available. That means you get GPS as your Navic both option. We already have the chip and given to the mobile manufacturer to implement their next generation mobile phone. And what is the things is that this all started sitting geostationary. We need minimum 4 satellites to give the position information and timing information. So from 9 we record 4 only, but redundancy we put 9. Okay. Next is the Indian Space Science Exploration Mars Orbiter Mission. India is the 4th country and first Asian country should send the Mars orbiter mission to the planet to Mars. This is the design for the first interplanetary. This is the first interplanetary mission of India, and it is the only orbiter that orbit around the Mars at an elliptical orbit. It launched in November 5, 2013, and he having that almost 5 payload to monitoring the Earth's surface, Mars surface, their chemical composition, mineral composition, image of the Mars using that payload, we able to get. If you see here the satellite, this is the solar array that generate the power for that journey, and this is the antenna. I told that Mars is almost 80 million kilometers away from that. For signal will come, we need very big antenna. That we put very big antenna. That is high gain antenna. But we need to fuel also go to the Mars. That way, big fuel tank also there. How we planned the Mars mission? How we can go anytime to Mars? No, we having some particular geometry. Then only we can go. If you see this picture, that mark one, this is Earth and this is Mars. And if you want to go from Mars, Earth to Mars, particular one geometry we use that, and with minimum fuel, that will come once in 2 years. So we taken the opportunity. We launch our satellite 2013, and initially satellite around the Earth, and we increase the maneuvering doing. After that, we send the satellite to the Mars to the elliptical path, and it will go there, and that time Mars will come there, and it will come there, and that time our satellite reach there, and they capture in the elliptical parts. I show one video on the how we capture the Mars.
The extended version of the Polar Satellite Launch Vehicle, known as the PSLV-XL, from Sriharikota, the spaceport of India. The rocket will lift off from the ground, using its first stage solid rocket motor, and the strap-on boosters. As it travels through the atmosphere, the first stage and the strap-ons will burn out, and separate themselves out of the vehicle, and the second stage liquid engine takes over. When the rocket then comes out of the atmosphere, the heat shield protects the light, the atmosphere will open out, and down. Subsequently, the second stage will burn out, and hand over the flight to the third stage solid rocket motor. The third stage will again jettison from the rocket, after completing its thrust phase. During the first 3 stages of the flight, is track down range stations,
This is a track of the satellite, how satellite is moving.
located at Bangalore, Sriharikota, Port Blair, Brunei and Biak, will track the vehicle, and continuously deliver the vehicle telemetry to the control
This antenna tracking the satellite by ground.
center. The rocket then enters a post phase where it follows an unpowered ballistic trajectory, for a duration of about 26 minutes. When the vehicle sets out of the ground station, there will be a gap of around 10 minutes where it will not be visible to any ground stations. Subsequently, it will be spotted and tracked by 2 shipborne terminals located in the Western Pacific Ocean, where the major vehicle events will be monitored. The first ship is
Actually, if you see that Pacific Ocean, there is no ground station. Though, then we send the 2 ships to monitoring that satellite. We are with accurate radar system, everything.
located at such a position, where it can monitor the ignition of the 4th stage liquid rocket engine. Similarly, the location of the second ship is chosen, so as to monitor the burnout of the 4th stage, and satellite separation. Finally, the solar panels will deploy for generation and supply of solar power to the spacecraft, followed by the deployment of the high-gain antenna, which will support deep space communication between the Earth and the spacecraft. The spacecraft will be injected into an elliptical
So first that spacecraft injected around the Earth, it rotated around the Earth now.
orbit of 250 by 23,000 kilometers. A series of
And that satellite having firing the fuel increase orbit.
orbit maneuvers will be conducted using the onboard liquid engine to raise the apogee altitudes. At the end of the fifth burn, the apogee altitude will be around 2 lakh kilometers. The sixth and final maneuver will inject the spacecraft into a hyperbolic orbit, in which it escapes from the Earth's sphere of influence and embarks on a heliocentric journey. The heliocentric phase lasts for about 300 days.
If you see, this is the Earth, this is the satellite, green is the satellite, and pink is the Mars is coming.
At the end of which, the spacecraft reaches the sphere of influence of Mars.
Mars.
The Mars orbit insertion maneuver will be performed at the closest approach point, thereby capturing Mars in a 375 by 80,000 kilometer elliptical orbit.
Okay, like that we capture the Mars, and this is the first country and first attempt we able to reach the Mars. Next, we having one more fascinating launching of the AstroSat. This is the first dedicated Indian astronomical mission satellite. You take the image, you having a lot of mainly ultraviolet imaging telescopes there. That you take the image in the ultraviolet frequency, and that is the you can see one Crab pulsar image taken by the AstroSat, and this was launched 2015 September 28. Next is the Chandrayaan 1 mission. This is the India first mission to go to the moon, and India is the first country at first attempt able to capture the moon. And it launched October 22, 2008, and this is only a orbiting satellite. There is no lander and rubber. It carried almost 11 scientific payload and made from India, USA, UK, Germany, Sweden, and Bulgaria. And if you see that Chandrayaan tells that presence of water at moon. This is the first country we are told that water is present on moon using the Chandrayaan mission. And this is the clean photograph of the Chandrayaan actual satellite. Now second is the Chandrayaan 2. They launched July 22, 2019. And we are choose Thursday. We land the south pole of the moon where nobody has gone before. What is the problem there? There is the sun in elevation very low. That is maybe 6 degrees, and power generation very low. So nobody attempted to land south pole of the moon. But we taken that courage to land that extreme condition, like a low lighting condition. We want to land south pole. And why record the Chandrayaan-2 mission? Because we want to improve our technology, demonstrate the technology for deep space motion. And we need to understand the space environment using this type of technology. EPC Chandrayaan-2 is consist of the three elements. First, orbiter. Orbiter is it orbit around the moon of 100 kilometer orbit, and he having the 8 payload, and he can generate 1,000 watt power using his own solar panel. They having solar panel generating the power, on power. And this is lander Bikram. That is they having a 3 payload, and it having 65 watt power he can generate. And you can see they also having on the panel, and this should land. This is lander leg. It should land the moon surface. And this is our program. This is sitting inside the Chandra lander. After landing to the moon, lander landing to the moon, it should come out from the lander. And it should be launched by our GSL Mark 3 Bahubali. It can 4-ton G2 satellite. This is called GSL Mark 3. How we planned the Chandrayaan 2? This is similar to our Chandrayaan 1. First, that launch is that around the Earth orbit, and it rotate around the Earth. Then it will go to the moon, and moon also it will capture by elliptical orbit. Then series of maneuver, it should go to the 100 kilometer by 80 kilometer orbit. From 100 to 80 kilometer orbit, lander should separate from the orbiter, and lander to land in the was planned to land to the moon surface, and from rover should come out. I think people think that since Chandrayaan on failure, I think we had a success. 99% we got success. The failure not due to any technical lapse or anything. This failure due to the one thruster. We having 5 thruster in that lander to reduce the velocity of the lander. They overperform. Due to overperform, that speed of Chandrayaan lander is reduced, and our time is fixed. It should reach particular point. So you want to increase the speed. So what he did, he rotated 180 degree and want to increase that speed. That time he lost the control, and it is the hard landing to the moon surface. But we understood the problem. I think Chandrayaan 3 will be great success in coming now. I want to show one photo of this. You see on a small video of the Chandrayaan 2.
Hi. Eight, 7, 6, 5, 4, 3, 2, 1. We have ignition.
Battery injected to the orbit. Main deployment. It already rotated around the Earth elliptical orbit, and in one liquid propulsion engine increase the orbit. Now it go to the moon from the Earth cavity. Escape from the Earth cavity, go to the moon now. Now it's captured by the moon by elliptical orbit. Now you make 100 kilometer of circular orbiter rotate that. Then lander will be separated from the orbiter. It will be land with separate orbit and orbiter with separate orbit. Here you can see that orbiter rotating in the 100-kilometer orbit, and landed over 180 kilometer over 100-kilometer orbit. And before landing, orbiter scan the Earth and Moon surface and find the greatest safe landing point. That lander having on camera sensor, they automatically detect the hazard. They find out which is the best landing site. You should land some ditch or some rock. You should land surface. So the one camera, one sensor, they detect all things and land the flat surface. The scanning is doing that. Sending the communication to the Earth lander directly. And it after 14 days. After 14 days, the sun will not be there. One minute. So, Chandrayaan 2, I think we had a success. 99% we got a success. Only 1% we got to get success. But we are sure Chandrayaan 3 will be the 100% success. So Chandrayaan 3 mission is the same like our Chandrayaan 2. Only our orbiter is still orbiting there and health is very good. Daily they're sending very good images from moon surface and a lot of experiment doing. So we're not sending that orbiter again. We're sending only lander and rover there. So this is the latest configuration of Chandrayaan 3. If you see, this is the orbiter, same like Chandrayaan 2, but we modify our orbiter. It is the only propulsion module. Propulsion module means what fuel required to send the satellite to the moon. So that much changing we are doing, and we are changing some logic inside the logic. Now, you remember that August 2019, our Honourable Prime Minister announced India will send a human to space by 2022. So our ISRO Gaganyaan project started from then onward. We're planning to send 3 crew members, astronauts to the space by our own launch vehicle, own crew module. If you see that left hand side, this is the launch vehicle, that is GSM Mark 3, and we modified for launching for the Gaganyaan by Human Space Program. And if you see right hand, this is the actual crew model. It consists of 2 parts. If you see first one, this is the crew model where the astronaut sit inside there. And if you see, and one model is the service model that have all power system, all propellant, everything sitting there to give that supply to the crew model. And if you see inside this image, not actually ISRO image, I taken from the NASA. Actually, these SpaceX images, and they're sitting inside 3 crew model, sit inside the this crew model, and they should have protect themselves using the space suit, and that is our future model 2022. So already I told this is the concept of crew model on service model, and astronaut sitting inside the crew module, and this is opening. They can see outside this opening, and they both is connected to the one connector plumb. And all thruster fuel will be the service module. This is the thruster used for the change the orbit, increase the height. It will be the and this is, should sit. It should land in the sea, soft landing to the sea. Now next one interesting mission coming, Aditya 11 mission. This is the first mission to study the sun. If you see sun photosphere, that is temperature around 6,000 Kelvin. But if you see outer region of the sun, the temperature more than a million degree Kelvin. Scientists don't know why this corona region temperature too much high. So ISRO had taken on initiative. We want to monitor that corona gap of the sun and detect why this temperature. We do that on scientific experiment. For that, we're planning the Aditya 11 mission. But if you want to monitor the sun continuously, we cannot use the normal orbit like a LEO, GEO, because this will be the around the Earth, and the Earth side will fall. We cannot monitor continuously the sun. So we find out some Lagrangian point in the space. If you see that Sun, Mars, Sun, Earth, and Moon system, in the space we are having the 5 point that is their potential is very gravitational potential is very low. That is called stable point. That is called L1, L2, L3, L4, and N5. If we put any satellite in L1, what will happen? It will continuously see the sun and it continues communicate to the Earth. So we want to send our satellite to this L1 point. If you see one more point, L2 point is the backside of Earth. That is always the shadow of the Earth. So no sunlight fall there. Normally all astronomical satellite, NASA sending, they're sitting there, this L2 point. If you see one more point, L3, we don't know what is the L3. This is always a shadow from, it should always behind that sun. So we never see what is there. People are telling there maybe the Earth-like planet is there. Lot of stories there. So we want to go L1. This is called this is 1.5 million kilometer from Earth, and we having one payload that is a visible emission line corona VLCC that is monitor that corona of the sun. Now come to the Indian space station. India can develop their own space station. If you see left hand image from the ISS, International Space Station, and if you know this is the size of this space station around 100-meter long and 80-meter width, and is weight almost 400 ton. And if you see if you develop this space station, and they're doing some lot of experiment, scientific experiment there, like zero gravity experiment they're doing there. But for that, you need to transfer that what do you call your astronaut service like fuel, all things. For that, we need the launch vehicle. If you see, this is the launch vehicle, and it go to the rock to the spacecraft. Both are moving almost 7 kilometers per hour. So both spacecraft dock together and supply that they are astronaut. This is a very difficult job. ISRO have already taken this initiative to develop this. So next mission coming, space docking experiment. There what we're planning? We're planning two small spacecraft go into space, automatically they dock together, they exchange their power, fuel, and again undock. So this we are planning to launch 2023. So if we develop this, we able to one candidate can go to the ISS, dock our satellite or launch our satellite and send our astronaut to the ISS. So we are in the way. I think 2025 we can get some testing. Now I talk about the ISRO launch vehicle development, satellite development. Now I come to what the unique space field. Anybody can do the space? No, you can. No, everybody cannot do space because this is the high value, high cost. So if you want to space, is a high costly element. Everything is very costly, and very few parties there to develop this space program. If you see India, there is no companies there to develop space program because there is very reliable. Reliability is very high, and so and high risk, very high risk. So very few fellows there to develop this space field. And it's a multidisciplinary action, a multidisciplinary things, a lot of science, everything include together. And if you see, space is a totally different environment. we cannot simulate full things in the ground because that minus gravity, zero gravity, and that vacuum temperature, you can everything cannot test in the ground. So we are doing simulation sending. That is also one more risk. It involves large of software. It involves lot of software and mission. You need a ground system which is having more complex than the onboard system, and we need a lot of we are using a lot of onboard operation and hazardous material to use this one. So this is a very unique field, so and very challenging field. And if you think so, what is the engineering required discipline in this field? Aerodynamics, flight dynamics and orbital dynamics, propellant, propulsion engineering, control system, structural engineering, material, mechanical system, thermal engineering, pneumatic hydraulic engineering, electrical system, cryogenic engine, fluid, chemical engineering, RF microwave, everything. If you think anything in the science, everything involved in the space program. And above all, science, physics. Without physics, I think space program cannot go ahead. So physics is the main things for the space program. Now, if you think what the opportunity will come, how to join the space program. For that reason, Department of Space established one institute called Indian Institute of Space Science and Technology, IST. And this is the Trivandrum. And this is the directly give the access to the Indian space program laboratory, everything. After study that, people directly join the ISRO as a as a scientist, and they offer a lot of varieties of sources courses like BSc, MTech, MSc, PhD, postdoc, everything they're giving. So this is a very good opportunity. People can join there and directly can absorb by the ISRO. And they can take a BSc everything, and all the ISRO interested. This is the all India exam is there. From through also you can enter to the ISRO. And for PhD student, we have been direct interview by your chairman ISRO. From that, they can join as scientist asset and the high level. So you have a lot of opportunity. You can enter ISRO by written test or any institute or any interview. And recently, ISRO that lot of private company coming to develop the ISRO space program, that space program. So you can join this private company also. Now this is started now. Now I'll come to my conclusion. If you think ISRO is one of the best space organizations in the world, India is the sixth country having in the world having the cryogenic engine technology. India launched 104 satellites in one go. This is the one record, world record. Nobody launched 104 satellites single attempt. India is the first country reached to moon as first attempt and discovered the water on the moon. India is the fourth nation to world and first nation to the send spacecraft to the Mars. In now, only 50 to 60 ISRO launch, 109 satellite, 77 launch mission program, student satellite, 2 re-entry mission, and 319 foreign satellite from 33 countries. Many complex missions is coming years like Chandrayaan 3, HSP, Aditya 11, SpaceX. I think best of ISRO yet to come. We are waiting for. Thank you very much.
Hello. Wow. Thank you, Mr. Maji, for your nice, exciting, and excellent presentation. We could gather a lot of information and details behind the different space programs and launch of satellites by the ISRO. We can know how gigantic effort, skill, knowledge, and teamwork is required for each space mission. This talk will surely inspire our students in the field of space science, and it will be really helpful to the participants to understand the activities, challenges, and various missions of ISRO. The student participants may also trigger themselves to pursue their career in space research at ISRO. We thank Mr. Maji for providing a guidance to those who wishes to get involved in these enormous activities of ISRO in future. So the participants have a lot of questions in their minds. However, we cannot convey them all to our respective school due to time constraint. So these questions have been sent by the participants in the Google Meet and YouTube live section. So can I continue? So can I continue? So can you hear me?
Yeah, continue.
Yes. So the first question is that how satellites are protected from solar flare.
Actually, solar flare is that this is an electromagnetic wave. So we having that normally what are doing? We having that MLI multi-layer insulation is there. There we cannot enter that high level particle to inside a satellite. We are doing radiation shielding. We are not using normal commercial component. We use radiation shielding the component. This is the called test qualified quality component. There also, if we high energy particles, nothing will happen. Sometimes what are doing? Like if you see the solar flare affecting too much, we orient the satellites a different way, such that it not affect our satellite. So we already taken care in our design itself.
Okay, thank you. And the next question is when the satellites are launched, we see that it is covered with gold, I think gold sheet. Why?
That is called multi-layered insulation. Actually, if you go to space, temperature is very low. One say minus 200 degrees C2. If sunlight fall, it will be plus 200 degree. But no component, no commercial component can work in that this high temperature range. So what are we doing? We protect that satellite from temperature things. This is reflected. If light will fall, reflected back and keep the inside of the satellite is normal temperature, like 0 degree, 25 degree. For that, this is called multi-layer insulation.
Okay, thank you. And another question is how the satellites can change their orbit and velocity. In the you have seen in the Chandrayaan or the Mangalyaan, they are changing the orbit and velocity. This is how you can do that.
Actually, every satellite having a fuel, they having a motor. On motor they having all fuel is there. Using the fuel and altitude, they can change the altitude. Every satellite having the fuel that is called liquid engine. Using liquid engine, they can change their orbit, anything.
Thank you, sir. Another question is in space there is no air. How can the thrust for the satellite be there? How can the satellite get the thrust in space where there is no air?
Actually, this is work on the Newton's third law. We injected something, it gives the velocity. We actually fuel is injected, that is the given the reverse velocity. That is called the momentum. So this is Newton's third law. It not depend any what do you call it, vacuum anything. This is the only working Newton's third law.
Okay. So another question is for solar mission, the position of the satellite at L1 is the gravitational force be zero. But for solar mission, you have shown that in the L1 position.
If you go to the L1, gravity is microgravity. This is from almost 1.7 kilometer I have from Earth. But there, whatever this energy is very stable. That point is called very low gravitational force. Potential is very low. That point is very stable. But gravity will be almost a microgravity, very zero almost.
Sir, ওই কোশ্চেনটা আমি করেছিলাম. So how can it get centrifugal force?
Can you repeat the question?
So if gravitational force zero, then how can it get centrifugal force or centrifugal force?
No, this is the like how you think it is like your rotating. It's not rotating about the earth, rotating about that point. This is go and step there. It's not rotating with the system. So it's not rotating around the earth, it's rotating about the sun. That is very stable.
Thank you, sir.
Another question is what benefits we can get from Chandrayaan 3 or what is the main objective of Chandrayaan 3?
If you know Chandrayaan 1, we first discover the water on the moon. Everybody send the satellite to the moon, but we are the first country develop confirm that water is the moon. Now second, the technology. Everybody going Mars, they want to make their colony there. We also develop our own technology. We can do mineral composition. What mineral is there? What composition is there? Like helium. A lot of helium is that Mars, moon. People want to bring from there helium to the earth to as a fuel. So we should be the challenge. We should be same level to other country also. So actually, the technology development you can tell.
Okay, thank you, sir. There is another question that is there any possibility of collision among the satellites rotating around the Earth?
Yes, sir. Actually, this is very much possible. If you see the Earth from the space full of debris only, So what are doing? What are doing before launching? What are doing? We having the tracking system. Every debris we having every number. We track that. We calculate the orbit velocity. And if one orbit, the orbit very much determined. It cannot go like not driving our road or normal road. We going any direction. But orbit there will be particular velocity, particular direction only. So we know that every orbit, every debris position very accurately according to launching our satellite. So we are doing the collision before launching. We collision. We are doing a lot of analysis before doing that.
There are lots of more questions are coming in the YouTube and Google Meet. And there's another. So can I continue on with few more questions?
I don't have any issue. You can continue.
Okay, thank you, sir. How thrust acts during gravity change from Earth to Moon?
Can you tell me?
I think they are asking that when we launch from for Chandrayaan, I think how the gravity change from Earth to Moon, the thrust due to the change of gravity.
And I tell you that thrust that liquid engine not depend on any gravity. That is only depend on that how much fuel the momentum. Fuel they rejecting fuel same some velocity they give reverse velocity. So thrust not changing. If you gravity changing, it will be 1/6. It will be the Earth to Moon will be 1/6 will be gravity changing.
Thank you. One has asked about Van Allen radiation belt. Can you say something
Yes,
about
yes, yes, yes. Actually, if you see, if you go to the space, space is very harsh environment, not like very simple. There is some belt that is called radiation belt. There are lot of high energy particles there. So this is called two types is there. One lower orbit is the higher orbit there. So what when we launching the satellite, we try to avoid this Van Allen belt. If you go to this belt also, we taken the consider how much radiation you get from this. We that much protection give our satellite to protect this radiation belt. So we taken care of that things also our design also.
Another question is that do you think that new private startups like Skyroot, Bellatrix, and Agnikul with their own launch vehicles be successful in the near future despite economic crunch
Actually,
issues?
we think so. Private fellows should come. If you see NASA not doing any launch vehicle development. They are giving to the private company like SpaceX. They are doing. So India also want to develop some private fellow who can develop launch vehicle, and ISRO it concentrate on that R&D activity. So we are planning the private fellow should come, and we are giving our facility to demonstrate that system. That way, one agreement happened between the private fellow also. They can use ISRO facility. ISRO giving training them to develop their own launch vehicle.
Okay. So funding is one of the problem. 1 minute. So another is asked that the biggest downside of our ISRO as compared to NASA is the funding or financial support of ISRO. So if ISRO has the budget as much as NASA has, then ISRO will be the number one.
I don't think so. I don't think so. Finance is the problem. Problem is that I think our manpower, our young engineers should come and join ISRO. What happen? Our scientists go abroad. Same scientists go abroad to join NASA. If they should come India, work for India, then ISRO can go. This not any financial financial things involved there. This is only technical things. We need young engineer, good engineers who stay in India, do work for India. Then only ISRO can go a very high level.
So we can encourage the students and the participants who are listening to join ISRO.
I can tell ISRO is one a great institute, not in the India, in the world. You get a lot of freedom, lot of work, lot of new activity you can do. And if the management is very good, if you compare any organization in the India, I think this is the best organization. There people get freedom, exposure, everything. So they should join. They should come and join ISRO. I think so. ISRO future is very bright.
So another question is, what is the highest limit in distance that we can catch any signal coming from a satellite?
Actually, that depends on the antenna size. Actually, we having a 32-meter antenna, and 32-meter antenna we can capture a signal from the Jupiter or Venus. If you want more, we need increase the size of the antenna, 32 to 64 meter. So Jupiter and Mars, Venus, we can get the signal. And we're planning Jupiter and Venus mission also coming years.
Okay, thank you, sir. There are still questions are coming in the YouTube Live and Google Meet. So do you India can have their own form of Elon Musk?
I think who is talking? They should come. Young engineers should develop their own startup and become the Elon Musk. You should read the Elon Musk history. How he developed that. People should read that one. The very good history. How first I think he launched. I think 4 or 5 launch vehicle. Everything is failure, and he don't have any money to next. He sold something, and he got after he got success. After this, see how where is he is now. You should read it. People should read the Elon Musk history. I think he's the one great fellow. I think people should read it. Young engineers should, young scientist, or anybody can read it.
Another question is what happens to the dead satellites? How long they stay in orbit, or do they burn out?
Actually, if it's this is depend on the orbit. If it's geo orbit, they continue. It will be almost 15, 20 years will be there only. But for a geo 24, 36,000 kilometer away. So what are we doing? We're changing the orbit. We're not giving 36,000 kilometer. We're changing the orbit some height. After it became life hover, we change the some orbit to feed that portion. And if you think Leo, if is that 400 kilometer to 500 kilometer, it is more than 10 years to 15 years. So space depth is increasing. Now we are doing one technology how to remove the space debris. So that is a big stream one stream is coming. How to remove the space debris. So NASA developed a lot of things, magnetic field, some net type things. You catch the satellite, pull to the Earth atmosphere, it will burn out. So it will according to orbit, it may be the it may be the what you can tell 10 to 15 years. And if you see the launch vehicle parts, it will immediately come to the sea. It not take maybe the 1 day, 2 days only. But satellite, it will be orbit 10 to 15 years.
There are still questions. So there are still questions are coming. The participants are very much excited for having you here in the webinar.
Thank you.
Yes, we have still more questions. So can we continue, or will we? I will tell that.
I don't have any schedule anything.
Yes, then it's fine. Yes, how satellites protects itself from comets and other space things?
If you see that comet and other space things, they having a known orbit. I tell you, the orbit is known, everybody. Not like our driving the car, means road. We can go any direction, but satellite or comet cannot come any direction. They come particular one direction, particular orbit. So before that, according to that, if we coming towards the satellite, we remove we deorbit the satellite some other position, parking other position. After comet pass, again come back to that position. You can do that maneuver. That is called maneuver.
Okay. So another question is it important to calculate the Lagrangian point for launching any satellite?
Lagrangian point is very much important for the astronomical satellite, like solar mission, like Aditya mission. Normally, when we want to stable point, like sun pointing, that way, normal communication satellite or LEO satellite should not go Lagrangian point. This is the specific satellite because that point.
And few are asking about how for career in ISRO, for after their graduations in honors or pass or after school level, how can they build their career in ISRO?
That actually after BSc and you can join through all in exam is there. You can join through this, and this written exam will be there. In the first will be written exam, then will be interview, and selected candidate can join the ISRO scientist. That a lot of option is there. Now I think you should start that website, ISRO website. They're giving that announcement when this opportunity come. They should join that time. They should apply that time.
If physics honors students will be
yes. I don't know. Without physics, physics student the master.
After graduation they can. Okay.
After BSc, after BTech, every point you having the entry point ISRO. Not like if BSc completed, every point having the entry point. You can enter any time into ISRO. If you write a student, we're taking a special interview and taking to ISRO. by our chairman.
And another question I would like to ask is my question that in the last few months back, there was a program where a missile was to destroy a satellite. If you give some light on that.
Actually, that is a defense thing, so I cannot tell that. Our aim to make the satellite. I will not link to our thing defense, but that is called anti-satellite missile. So I cannot talk on that things, I think.
Okay, sir. Thank you. Thank you, sir.
Thank you.
So we thank you to Mr. Maji for giving his valuable time to enrich us in the field of space science. We also wish ISRO to carry the baton of their success as usual in the future. And now we have a small announcement.
শুভদীপ, তোমার সাউন্ড কেটে যাচ্ছে। শুভদীপ, তোমাকে শোনা যাচ্ছে না। অর্জুন, অর্জুন, হ্যাঁ, so you can conclude now. Vote of thanks.
Very good evening. We must say excellent, amazing, and fabulous after such a nice presentation. Now we are at the end of our webinar on exploring the sky from Aryabhata to Chandrayaan. So firstly, we thank our eminent resource person, Mr. Amit Maji, for delivering an excellent topic, which is also a matter of pride and prestige for any Indian. We have listened to the glorious journey of Indian space organization over several decades. We have heard the challenges behind the projects of Indian space programs. We think it is a high dream for any student of science to get an opportunity to being associated with such challenging project of our nation. Mr. Maji has put the right kick to our students in this pandemic situation by motivating them through this webinar. So, this webinar is successful to reach our goal of enhancing the motivation of our students in their future study. Now, we express our thanks to Dr. Sofon Niyagi, officer in charge of our college, who has constantly inspired us to arrange for such kind of motivating webinars that will charge up the students in this pandemic situation. We are also thankful to Dr. Honourable, IQSC coordinator of our college, who has guided us to arrange this seminar and helped us to sketch the program schedule. We are thankful to Mr. Arjun Das, Assistant Professor in Physics, for execution of technical part, including registration of participants and monitoring the Google Meet and YouTube Live system at this present time also. Our thanks to Mr. Nirmalendu Hui and Dr. Subhodip Nath, Assistant Professor, Department of Physics, for their constant effort to make the seminar success in all respects. We also thank Dr. Hiranmoy Pal, State Aided College Teacher, Department of Physics. We convey our great thanks to all the participants for showing their interest to this webinar and their patience to make the webinar successful. We also congratulate all the faculty members and non-teaching staff members of our college for being with us. Once again, we express our sincere thanks and gratitude to the speaker for spending his valuable time with us by managing his busy schedule. Now, taking the permission of our honorable officer in charge, I conclude this webinar here. Thank you all. Hope to see you all in the next time. Thank you.
Thank you.